Hi and welcome, ladies and gentlemen. Today we are talking about M-Ary trees. Well, an M-Ary tree is a data structure that is, you could see it as a generalization of a binary tree, or that a binary tree is, a special type of M-Ary tree. Well, it is used for storing data, it is very efficient in search, and it can be even made more efficient if we use some derivatives of the M-Ary tree, like the B tree, the B star tree. The binary search tree, for example, is a derivative of the M tree with n equals 2. Or there are some more, the AVL tree. I made videos to them, I blend them in bit by bit here. Alright, the main usage of the M-Ary tree is in databases, where the keys of the tables are stored in those B trees or B star trees, which are special types of M-Ary trees. And that is used for a real efficient search and insertion and all the operations on databases. But that is only one example. There are so many examples for that. It is merely incredible how many good applications we'll find for those M-Ary trees. And as I said already, the binary tree is one of those, and that is usually the basic example. Alright, so let's have a look a little bit deeper into those M-Ary trees and how they are defined. Well, an M-Ary tree has a root node, and each root node has m children. And each of those m children is then an M-Ary tree by itself again. So, and one condition is there that there is no circle within those trees. Well, let's have a look here. Well, we have the root node 1 and the children. This is a ternary tree. The root node 1 and the children 2, 3 and 4, as we see here. And each of those children has 3 children again, and like this it has their trees by itself. So the 2 with the children 5, 6, 7 is a tree, the 3 with the children 8, 9, 10 is a tree, and the 4 with the children 11, 12 and 13 is a tree. I have to say those trees, so the number of children, doesn't have to be complete. It really depends on the order, how you insert them and stuff like that. But I usually insert elements in a regular M-Ary tree in Breadt's first traversal order, meaning that I fill each layer from the beginning to the end, and then I keep going with the next layer. So let's have a look. Oh yeah, here you see the third tree with 4, 11 and 12 as the children. Alright, so let's have a look at the list representation. Basically, we can say that we have an item that is a root, it stores some data and also the pointers to its children. And with that, we can traverse through the tree pretty easily. It has also an array representation. I made a video on the array representation of binary trees. I blended in here. So it is kind of similar, just that we have m children. Alright, so let's have a look at the Breadt's first traversal, because that is usually very interesting if we want to insert data into the tree. Well, we start with our root node and we put that in a queue. And then we put our result as an empty list. And then we go through it and say while our queue is not empty, we put our children of the node. Obviously they have to exist. It is not allowed that there are none, otherwise we will run into an endless loop. But we enqueue them to our queue, and so we basically run from the beginning. We have our root node, then we have the children of our root node, then we have the children of the first child of our root node, then we have the children of our second child of the root node, and so on. And we do that for all the nodes in our tree. Alright, so let's go ahead and implement that. For that, go in Visual Studio Code and I create a new file called M-Ary tree.python. And there I create a class called M-Ary tree, and that gets a node class. It's a helper class that is responsible for storing the individual children of a node and value. So let's create that. I say class and I make it private. That's why the two underscores are there, and I call it node, and that gets a list of children, and there I initialize that with an empty list, and it gets a value, and I initialize the value with none. And then I want to have a constructor, which we see here with the init method, and that gets self and as well a value and m. I use m here because I want to initialize the list with an m none element. So we say here at first self.value equals to value, and then I say self.children equals to, and there I say that is none times 10. And with that we have initialized our list, not times 10, times m. And with that we have initialized our list with n none elements. Alright. Then I want to go in and create a constructor for our M-Ary tree, because that needs to know m. It will have m as a property, so let's write it down. M. We initialize it with none, and it needs a root node. So we say root equals also none for now. And then we put in a constructor just to set n, because n is really necessary for the M-Ary tree, so we know how much children each node has as a maximum. So we say def init, and that gets self and m, and there we set our m self.m equals m small m. Alright. And then we create our insert method. So we say def insert, and that has again the self attribute and a value. And let's do some documentation here. And we say inserts a node in Breadt's first traversal order. Alright. So good so far. At first I want to check if the root node already exists. If not, then we create the root node and we are done. And if not, we have to traverse through our tree until we find a leaf node that is actually none. So we go in and say if our self.root equals none, then we go in and say here that self.root equals, and there we create a new node with our node class, and that gets the value and it gets self.m, which is a property of our binary tree. Alright, so when we are so far, then we can return here already. So you return here, and then we are done if it was a root node. Otherwise I want to enqueue all the children and so on, and then I want to traverse through this whole tree. So it is basically a binary breadth first traversal. So let's go in. We say our queue equals, and we can initialize it with the root node. So here we say self.root, and then we go in and say while true, and we will use an exit condition, which is in the end a break. So, or otherwise we can also say here while, let's do a boolean, and we say inserted equals false for now, and then we can say here while, and there we say inserted, or well, not inserted. Alright, let's go in, and there we say At first we need to extract our actual node from our queue. There we say node equals, and we take Q0, and then we can remove this node from our queue because we will be done with working on it. So we can say here Q equals, and there we take Q without the 0 element. So from our first element on, and lists are indexed by 0, so the first element is actually our second one, if that makes sense somehow. Anyway, so then we go in and say for, and there I want to go through our M. And so I say for E in range, or for I in range, and there I say self M. So we basically go from 0 to m-1 because this number you put into range, if you write it down like this, is exclusive. So we can say here if, and there I want to have a look, node.children, and we know it is initialized. We did it up here in our constructor method of the node. If node children I, that is our current index, is equal to none, we initialized it with none, so if it is none, then we want to create there a node. And there we can say node.children, and there we say I is equal to, and there we create a new node. And we give it, we want to give it the value, and we want to give it self.m, which is actually a property from our M-Ary tree. And if we did that, we can set inserted to true, and that will then stop our while loop. And I want to make a break here because we inserted something, and that means we can also stop with our for loop. So the break actually stops our for loop here, and the inserted property of our method will stop our while loop here. Okay, otherwise we say else here, else. Then we want to append this child to our queue. So we say queue.append, and there we say node.children, and there we say I. And I see that I have a misspelling here. It needs to be children, not children. So we are done with that now. And that should be fine to append elements to our tree. So we can insert elements now. Let's go ahead and write a short print method. For that I say def print, and there I gave it just a self method, and we can say here a documentation and say print the tree in BFT, so breadth first traversal order. And it is just a preference of mine to print it like layer by layer. But you can obviously do it in any way you want to, in breadth first traversal or whatever. So, alright, I think I have something like this in a video, and this video should be my binary search tree video. I link it up here, have a look there if you want to have a look at the print method in the depth first traversal. Alright, so let's go in and do that. And here I want to go do basically the same as in the insertion, but I will alternate a little bit the for loop down there. So I say here if our root is none, then I actually want to print none, and I want to return, because then the tree is empty and yeah, we are done with it. Otherwise I create a queue again, and that queue will be again initialized with the root node. So I say root here, and then I go through and say while, but here we have a little difference, and I want to go through while the queue is not empty, and there I say while q is greater than 0, or the length of our q is greater than 0, so the q is not empty then. And then I want to go in and print our element. So I go in and say node equals, and there we take the first element out of our queue again, and then we can remove it from our queue. So we say again here 1 to the end, and then we go in and say for each child, so for I in self.m, and there we want the range actually. And then we go in and say if our child is not empty, so if node.children, and there we say I is not equal to none, then we want to go in and append it to our queue. So we say q.append, and there we want to say node.children. And there we take the iChild. Okay, so we are done with that. That should be fine. So we append the children there, and then we just need to print our node. And there here we want actually node.value. So that should be fine. And let me have a look here. If node equals none, then we go in and append it. And if it is not none, then we want to append it to our queue. Alright, that should be fine. Let's check out if that works, and it hopefully does. And there we want to check again for main. So we go in and say, at first we create an M-tree, which is an M-Ary. Here we have a tree, and I want to, let's say 3 for now. And so we go in and then we need to fill it. So we go in here and say for I in. And now I say range 1 up to 30. And I say M-tree dot insert, and I say our I. And then I go out and say M-tree dot print, and that should be fine. Alright, let's try if that works. And we go in, it takes a second, and so we go in and print our whole tree in Breadt's first traversal. That works. Alright, and that is basically it, and the same way as I printed, you can also, for example, search in the tree if you want to. And yeah, so that is a basic way. The better way for searching in such a tree is usually the first traversal, because you get into a time of log n, in average and in worst case of n. But yeah, that's how it works. If you like this video, give it a thumbs up, and yeah, check out other videos on my channel, subscribe to the channel, so you always get informed whenever I'm uploading new videos. Alright, that's it for me. Have a great day. Bye.